Hello guys, welcome to Backbencher Studies channel. In the last video, we solved a problem on plotting the root locus if the open loop transfer function equation is given. So here in this session, we'll be solving another problem in drawing the root locus for a given transfer function. So let us start our session. So we have the open loop transfer function given. So we need to sketch the root locus of this closed loop transfer function and we need to predict its stability. So let us start doing our analysis. So what does the step 1 suggest? Step 1 suggests that the number of branches of root locus is actually the number of poles the open loop transfer function have. So if we see this order of this uh, denominator polynomial of open loop transfer function equation. So if we see that we have the order of highest power is s power 3. So we have three poles which are at s equal to 0, one at s equal to 0. And if we kind of do the arithmetic and find the roots of this equation, this quadratic equation, then we have minus 1 plus j and minus 1 minus j as the open loop poles for this system. So we have three poles, one at s equal to 0 and s equal to minus 1 plus j and minus 1 minus j. So, so we have three branches of root locus. So moving on to rule number 2. Rule number 2 states that the number of branches which are going to infinite is equal to p minus z, where p is the number of poles and z is the number of zeros. So we have no zeros and we have three poles. So we can say that three branches, all the three branches which are starting at these corresponding poles are leaving to infinite. So that's what rule number 2 states. So if we plot this poles, we have a one pole at s equal to 0 and another pole at s equal to minus 1. The real part is minus 1 over here and imaginary part is plus j, and minus 1 minus j over here. So this is all, and all the three branches starting from these three poles are moving towards infinite. Uh, they may be going to infinite in several directions. So in the next step, in the next steps, we'll be solving how they are actually moving, how the asymptotic angles look like. So moving on to step number 3, the real real axis, how whether it is present on the root locus or not. So if we see this if we see this part of the real axis, so we have the consider any point over here. So to the right of it we have only one pole, so which is an odd number, so thereby making this entire portion from here to here should lie on the root locus, as the number of poles, total number of poles to the right of it is an odd number. And if we see this, consider a test point over here, then the number of poles, total number of poles and zeros is equal to 3. So thereby making it an odd number. So we can say that this entire negative real line is lying on the root locus. So this entire negative real line is lying on the root locus. And moving on to step 4, we need to find out the asymptotic angles. So let us do that. We have the p, the number of poles is equal to 3 and we have the number of zeros equal to 0. So we have, if we substitute that for q equal to 0, we have 60, and for q equal to 1 we have 180, and 2 for we have 300 degrees. So this is kind of similar thing what we have done in the last class. So, and moving on to next rule, that is the centroid of these asymptotes. So if we do that, sum of real parts of poles minus sum of real parts of zeros. So we have a pole at s equal to 0 if we see that. So we have a pole at s equal to 0 and we have poles at these two places. So we need to take the real parts only. So 0 and this real part is minus 1 and this real part is minus 1. If we add that, what we have is minus 2, and we as we don't have any zeros, we substitute 0 over here and what we get is minus 2 by 3. So minus 6.67. So this is how where the centroid is lying, and if we draw asymptotes, then this is 60-degree asymptote and this is 300 degrees asymptote and this is the 180-degree asymptote. So moving on to next step, that is the breakaway point. If we see, if we do the similar kind of analysis, so what we have the is the characteristic equation, which is equal to 1 plus k times g times h. So if we substitute g into h as the open loop transfer function, we can find out the characteristic equation of closed loop transfer function. So if we find out the k in terms of this characteristic equation, what we have is minus s cube minus 2s square minus 2s. This is what we have. And on differentiating with respect to s, we have a quadratic equation in S. If we solve this, roots of these quadratic equations are minus 0.67 and plus minus j 0.47. So if you see this, these are complex roots, which states that there cannot be multiple breakaway points as per our poles pole zero concept. So there is no breakaway point in this problem because we have an imaginary breakaway point over here. So this is the test, because for this point to be lying on root locus, because breakaway point should lie on the root locus, so it should satisfy the Evans conditions, that is the angle of this angle of gs into hs at this point s equal to this point should be an odd multiple of 180 degrees. So if we substitute this and if we find out the angle, what we have is minus 164 4.11 degrees. So this is not an odd multiple of 180 degrees. So from this we can say that this point is not on the root locus, as it is not satisfying the second Evans conditions, that is the angle criteria. So we can say that there is no breakaway point. And if we see from this graph that the root locus definitely should intersect the imaginary axis so as to make this line as these lines as asymptotes. So we should find out the intersection with the our imaginary axis. How we can do that? That can be done based on Routh array. So this is the characteristic equation. If we make the Routh array for this characteristic equation, what we have is s cube and s square and s power 1 and s power 0. Alternatively, we have to write and 1 and 2 and 2 and k. That's what we have. So if we write that and if we do a similar kind of analysis, that is 2 into 2 gives us 4 minus 1 into k gives us k by divided by 2. That's what we have, and we have 0 over here. So for the system, if the system is touching the imaginary axis or roots on the imaginary axis, then it is said to be marginally stable. So for that marginally stable, the entire row should be 0 so as to get the auxiliary polynomial. So for that, the k value for which the system is marginally stable, that is found out by equating this to 0. so as to this entire row would be 0. So if we do that, what we have is k equal to 4 as a threshold value for the marginally stability condition. So if we find out the auxiliary equation, that is the one row behind this entire row 0, zeroth row, then we have the auxiliary equation as 2s square plus k. If we substitute k equal to 4 over here, we have two roots which are plus minus j 1.414. So these are the points where the root locus intersects with the imaginary axis. So we are done with all our steps. So let us plot the root locus. So we have uh, we have asymptotes at 60 degrees and 300 degrees and 180 degrees, and we do not have a break-even point, but we have a centroid at 0.67, that is the intersection of these three asymptotes. And we have the intersection with the imaginary axis as minus j 1.4 and plus j 1.4. If we do that, do the analysis, so it seems that the branch which is starting at this pole at s equal to 0 is going in at an asymptotic angle of 180 degrees, and the pole which is starting at, so the root locus branch which is starting at this pole is kind of moving asymptotically like that, intersecting at 1.414 over here. So it should touch this in such a way. So how it is going, so let us derive that based on angle criteria or angle of departure, whether it is going in this direction or in this direction or in this direction. So how it is going, we are not sure about that. So to do that, we have the angle of departure. So the angle of departure of this pole is the 180 minus the summation of all the angles from this pole. So 180 minus the summation, if we take, then this angle over here is 135 degrees with respect to 0, and this angle is 90 degrees. So if we substitute that, then the angle of departure would be minus 45 degrees. So a plus positive angle refers to the anti-clockwise direction and negative angle refers to clockwise direction. So starting from the horizontal real line, we should go 45 degrees in clockwise direction. That is the the root locus, the angle of departure in this direction, minus 45 direction. So if we do similar kind of analysis for -1 and -j, then we have the this as 180 plus 45, 180 plus 45 giving us 225 over here. And if we do similar angle with respect to this pole, we have 90 degrees. So if we kind of substitute that, we have positive 45 degrees, because if we do similar kind of analysis for this pole, we get 45 degrees. So this is how our root locus will be looking we will be looking at. So this is how it is happening over here. So it is moving in such a way direction that it is making an angle of 45 degrees, and it is making an angle of 45 degrees. And these are the root locus branches going to infinite with an asymptotic angle of 60 degree and with an asymptotic angle of 300. And actually this region is also lying on the root locus. So the branch which is starting at s equal to 0 is proceeding to infinite at an angle of 180 degrees, just like that. And this is how the root locus can be plotted based on the following rules. So that's it for today, guys. Thank you for your amazing support. Please do share and please do subscribe our channel.